Hi everyone, welcome to the last the third or fourth stellar lecture series this semester. So this week's talk will be given by Professor Albert Zylstra. Professor Albert here is a member of the International Astronomical Union as well as the Royal Astronomical Society, and has sorry, I'm just looking at my notes here. Can't find anything. But he will be giving a talk today on supernova 1181. And hopefully you all know a lot more about supernova 1181 at this talk. So without any further ado, welcome, Professor Albert. You may begin.
Thank you. Yeah. Okay. So no problem here. For the people in the front, be aware that the light is positive. That's why I sneeze. It's wrong very long. I'll be talking about a bit my recent research. As often with research, it isn't a conclusion. I'm trying to show you what is the problem, where it got. But sometimes you do research and you think it's pretty nice what you found, but then you have to do a lot. There's still more to do. There's no final bottom line to this. I'll talk about something that's called ILOT. It's more interesting than the word sounds. I'll talk about one star in particular, CK constellation of Walker. And its association with Nova 1670. Yes, 1670 is the date, the year. Then I talk about Parker star and its association with the supernova of 1180. I'm old when I look for this. I don't think well. This talk has a lot of collaborators. Martin Hajduk in Poland, Quentin Parker of Kong, Stuart Irish from Wales, and many others. Research is no longer done individually. They always work in teams. And to start with something I'm a bit character say because this department now at the end of the COVID epidemic has not come in one scale. Certainly the astronomy group is not one of our attention. So I tried to put him in a narrow the picture of him. He was very shy. So this is the only picture we have of him. This is very shy. Taken about 30 years ago. Let's go on to the talk. If you look at the Milky Way, what do you see? Well, that's not a lot. Yeah, it's very clear weather, you don't see a lot. Go to the Southern Hemisphere, and what you see is very impressive band. Pick a filter that picks out the line of hydrogen alpha. And one of the lines of hydrogen. And you take out all the gas between this. And suddenly what the Milky Way looks like, and obviously this is a telescope, is a band of nebulae, nebulosity. A band of and I wish I knew how to turn the lights on. Does anyone remember how other lectures do that in here? No one had done the second lecture here? The system has changed since the last time I was here. The light buttons have disappeared. Yeah. So this one somewhere, I know, just don't know where. Yeah. If I get it back. Look at those nebulae in detail. Yeah, and that's zoom in. This nebulae in this particular case is very symmetrical. They're not circular, it's elliptical, but clearly it's a very nice. The colors here are green. It is done through those actual filters, the active colors. Those are different lines of ionized species. And the blue is oxygen, the red is hydrogen. And indeed, the oxygen lines are stronger at the center of the nebula. I can zoom in even more. And what you see is absolutely amazing. And these kind of nebulosities are amazing in contrast. What you see here is a nebula that's been ejected by a star right at the center, which you need very good eyes to see on a telescope to still see it. It is still there. It's not that long ago, in the past few thousand years, since the Ice Age, the star has ejected most of its mass, is now in a shell around it, and is left just a stellar remnant. I make my living studying objects like this. You think I make my living teaching people. That's also true. But I think they pay me more for studying objects like this. So these kind of nebulosities ejected by a star trace the endpoints of stellar evolution. So this is stars, the end. Nice one to begin with. Yeah. What is the end product of stellar evolution? Well, it depends on how star you are. Yeah, if you have a low mass star, then you end up, well, even with a disappointing name, a white dwarf. Sorry, these names are a century or more old. Nowadays, we obviously don't have to call anything a white dwarf. That is not politically correct. First of all, it has a color. It's discriminatory. It has something about the size that is discriminatory. It's worse, some stars are called red giants. Or they're also brown colors. Yes, nowadays we can play big names, but I'm afraid these are historical. We know what they mean. So a white dwarf comes from a low mass star. Star like the sun. It has used up all its hydrogen and its energy. Now left with just carbon. It is no longer generating energy, it is sitting there. And it's still maintaining its shape by something that's called degeneracy pressure. The pressure is so high that electrons can't physically get closer together because the uncertainty principle stops. The uncertainty principle, electrons have to be in different quantum states. Yeah, otherwise they can't exist, they can't share the state. The terminals, not bosons. Well, you can't make the white dwarf any smaller, you would violate that. But for a low mass, if for an intermediate mass star, say 10, 20 solar masses, but then you end up as a neutron star. A neutron star use up everything, and then one step further and change all its elements purely into neutrons. But then you have a bit of electrons. How do they do that? They just push them into the protons. And then you get all the neutrons, suddenly everyone is happy again. And get a much denser star consisting of neutron. Sometimes in networks, you've got even more massive star, and that is not stable. They end up with a black hole. Now, that is the only term I think which is politically correct. There are no people in the world who would be thinking that they're called black hole. This one is safe. And that will end up with ions. So that is the end product of stellar evolution. How they get there, of course, differs per type of star. For the type of stars I look at, this is ejection, but a very slow one that takes a few thousand years. But the ones that people are most interested in are the ones that are explosion. And then two types of explosions. You've got a supernovae, super new star. It should have to be a new superstar. And those are destructive events. That is when the star blows up completely. And the pressure of an explosion in the center forms the neutron star and the black hole. Everything outside is blown off. There are two types. Type 2 is called core collapse. And that is when the whole core just collapses. That's the term. That's what forms a neutron star. There's also so-called type 1a. And that is where you have a white dwarf, which somehow has managed to get a little bit more mass. It's accreted from somewhere, and it shouldn't have done that. It becomes unstable and decides to go for a neutron star. But it can't do so. There is an explosion, carbon ignites, and the whole thing blows apart, leaving nothing. Except for the supernova. The two types of supernova. And then you got the novae, just new stars. That's a funny thing that happens on the surface of a white dwarf. As the white dwarf collects a little bit more material, comes an hydrogen layer. At some point, there's enough hydrogen layer, everything goes back. Thermonuclear flash. The one that Putin is strength. So that's a flash on the surface of a star, the star survives. And and do it again and again and again. The supernovae are brighter, and with super gives you a hit. So that's what most astronomers would like. Astronomers love things that go bang. And that's why we've got a big bang. Yeah. If you wonder why the star has so many cosmologies, it's because the word big. And bang. What do you want? But I don't like them, and I don't bangs it a little smaller. Okay. And they're closer by. So here's a list of supernovae that have been seen in the recent past. And seen literally means that with the naked eye. Many of these predate the discovery of the telescope, ends of the telescope. Anyone? So the first one that they're actually all the ones known, but the one near 1006, the brightest one known at the moment, it reaches the magnitude of -7. And that is about 20 times as bright as Venus. Venus is bright enough to cast a shadow. If you're in the right place, at the dark enough place, I've seen the shadow once. Very faint. But that's all I've seen. And I've seen Venus in the daytime. You can do so under good conditions. This one was far brighter, and so it was easily visible. And this seen mainly in China and Korea, I think as well. One in 1056, that's 55, that's wrong. That is the one that formed the Crab Nebula. A little bit fainter, but still bright enough to be seen in the daytime. This one is even seen in Europe, very unusual for this astronomy event in the Middle Ages. It was seen in America, by the American Indians, natives, but mainly again in the East. 1181, that one was faint, with the magnitude of about 0. So it's bright as quite a bright star, seen in China and Japan. Then nothing for a while. 1572, the Tycho supernova, was seen in Europe. The name gives a hint. 1604, one from Kepler. 1618, there was a supernova. We know that. It formed the remnant, we know, but it was not seen. Don't know why. And then the last one was in 1987, only +3, and it was in the night as in America. So further away. But it was bright enough to see it. Discovered by 3 different people in 3 different continents. I think I've met all 3 of them. All 3 of them do little else than talk about this discovery. One of them can lift the lenses. Obviously, didn't see it out there because from the previous life. So those are the supernovae. Okay, not the only events that enter the sky. And this was a surprise that happened about 10, 20, 15 years ago. When was it? 2006, I think, 2007. And when the star near the center of the Milky Way suddenly got blocked out. And we have monitoring programs. We look at the center of the galaxy all the time. And so at some point, this was picked up that this star was brightening. And suddenly it went, and then it came down again. And it went brighter by a very large factor, by a factor of 5,000. And it wasn't an explosion. So Roman Villenda published a paper on it, and he showed it was a merger of 2 stars. You could show that because they measured the velocity of the star, you could see us from orbit, and the orbit was getting narrower and narrower. After the event, so yes, one of the stars cannibalized the other. So, the energy of that collapse, it's a gravitation energy, get deposited at the surface of the star, so instantly makes the star very hot. And that is what happened here. So these are also very spectacular events, and they're not explosive. From Solar, another collaborator of mine, and came up with an idea that they put all these objects in a diagram that has the time scale. How long does it take? Here's 100 days, here's 1,000 days. Again, the total energy that the event emits. Here is a unit of ergs. We don't use joules very much in astronomy still, but it's a logarithmic scale. Here you've got the supernovae, nice and bright. Here you've got the novae, much fainter, but there are many objects with luminosities and energies in between. And this object I just showed you is over here in that band. He calls them intermediate luminosity optical transits. That name hasn't survived. It's now known as luminous red novae. They're not novae. They are luminous, and sometimes they're not novae. And he proposed that all of these objects could be explained in two ways. Merges, they come together, and for very massive stars like the Carina, just an adventure in the star itself. It becomes unstable. Yeah, sorry, we need to find out how the light works in some things. I think that's the first email I want to write after this talk is trying to find out how to operate the lights in this room. So these luminous red novae, the very massive stars that have the Carina are getting the exception. So let's focus on the mergers. It is probably the majority of these type of objects. The luminosity comes purely from gravitational energy. Oh, you found it. Yeah. You see who needs lecturers? Luminosity comes from gravity, gravitational potential, in fact, it's a ratio. You say, oh, that's gravitational energy. That's what the star is. Yes, it's gravitational. It's very long. It gives a very fast brightening, but then quite a long-lasting decline to the luminosity. And that can take months, it can take years. It's okay. However, it has a star that lasts almost degrees of freedom. It can be a normal star, it can be sun, it can be a white dwarf, like this kind of star. It can 1 solar mass, 10 solar mass, 100 solar mass. So there is a very large degree of freedom with one star. Having 2 stars, well, this is quite a problem. So the number of degrees of freedom that you have is very large, much larger than 1 events. So every merger you will see is going to be. That's the problem. How does science work? Well, remember, science operates by having the data and the model. If you have just the data, then that is just the step. Otherwise, steps. Okay. Yeah. But you don't learn much from it. You don't learn how stems are made, why they have that shape. Just like the pictures. I like it. You need a model to explain what you're seeing. So here is a curve. And your data is actually comes from a resonance curve from nuclear physics, but that is irrelevant. How do I model this? Well, I look for something that looks like this. Like an elephant. Well, it's not far off, is it? I have to put that tweak the line a bit to make it okay. But that's fine. If you're a particle physicist, you're allowed to change the data to make the model fit. It's called string theory. But science needs it more than that. You need a prediction. So what do you predict? This is science. This is what I want to do when I have too many recently. I want to clean up. Going circle though, it makes some predictions. And he said that you should have nebulae with an inherent velocity distance. Because it is an explosion. If something is twice as far away, it must have moved twice as fast. And that is the linear velocity versus distance. He predicts that the nebulae will be bipolar because of the, if you have a merger, you've got a lot of angular momentum that you don't know what to do with. He predicts outflow velocities between 100 and 1,000 kilometers per second. And finally, he said kinetic energy is spread between 10 to the 39 and 10 to the 42 joules. If you put it in English, translate it to joules. Okay, let's start with the talk. How long do I have? Do I have to finish at 1 or can I go on to 2? Okay, yeah, but at what time? After an hour or after 45 minutes? Okay, so I'll be fast. So this is the CK pole. It was an object discovered in 1670 by Johannes Hemisphere. And he saw brilliant things on the sky. I'm not sure if it was all there. It's a Cygnus, the constellation, and it was a nova being here, but here is nova 1670. The new star that happened. It was discovered in June 1670. At a magnitude of about +2. So fairly bright, but not exceptional. It was a new star among quite a lot of stars. It was visible for a while, and towards October it was gone. So far, no problem. But the next year, in 6071, it reappeared, and it was there again. And now it even got a bit brighter than before. And it stayed there like August and had enough, and it disappeared. And in 6072, it did it again. Although by that time it got very faint. It was so barely visible towards the radius. And this is something Novae do not do. They don't explode 3 times in 3 years. So even all catalogs list this as a nova, there is no way it is. Mike Starr, who works at the Natural History Museum in New York, interesting, very nice office that he has. I gave a talk there once, and from the top you look down on the big dinosaur. You wonder which astronomer was that. He knows some astronomers called dinosaurs. He found that there was a very nice nebula at roughly the right position. And he said, well, that must be the remnant of that explosion. And he said, well, there's a ring here, there's a star over here, this star must have been the nova. That was a while ago, and we had a chance to get some new images of this object, maybe 60 images, and we found that this star wasn't a star. It was just another part of the nebula. And what we found was a very nice bipolar rock-shaped nebula. Here, this normally was what Mike called the star, and clearly it is extended, it's a nebula. And there is now a bigger ring still very clear around it, but it was very hard to make sense out of this one. What happened? First of all, was it the object from 67? This nebula, this image was taken something like 20 years after the previous one. So what Martin Heidel did, and I know Martin because he was my PhD student from before, he then gone back to Poland. And then he contacted me that he had this image of CK Volvo, could I help him with it? Well, I think he did all the work himself. I'm not sure I helped him much. So here is the image that he created. Okay, that's the tip of the lobes. You see something else that's interacting with something else, and there's a shockwave moving through. What he found was that these 2 objects over here, the one over here and the one over here, had moved with respect to 20 years before. That is shown here on the. This was the direction that they moved in, and then it was easy to calculate back where it come from. And it come from just the bottom of this bright part of the nebula. This is what Mike Schrader called the star. It's clearly not where it came from. You also have the velocity, because you see over 20 years how far it moved. You can calculate that, and we found, yes, this had come from the 16th century explosion. It was the right object. It was an explosion. But I don't know of no nova that has left any nebula ever like this. In fact, no nova leaves a nebula you can see even after a decade, let alone after 300 years. This was something else. So we got some data out of the ELMA telescope, the big telescope that operates in the millimeter, sub-millimeter radio. The Atacama Desert in Chile. What we saw there, well, was quite amazing. I didn't expect anything like this. Here you can see the lobes that Martin had found originally, and the structure around it. The white contours is what we saw before. Here it is blown up in more detail. We saw a very compact disk around it. In the center, there's a radio source right at the center, which you see with our own Merlin telescope. But there is nothing there. There's nothing visible. And then there is clearly a second bipolar lobe at a different angle than the first one. And the disk is on a certain angle. So something is very strange going on. It has several bipolar lobes. It is precession. The precession is because it's being emitted in different directions. So there's been more than one event. And to get precession, you also need to have more than one object in angular length exchange. There's a precession of the Earth. It comes from interaction with the Moon. So whatever happens here, you have to have at least 2 objects, otherwise it's not going to work. Then Kvinsky came along. He does not about TV, it's a entirely different thing. He got a very deep radio spectrum, and he found all kinds of lines that he could identify them and blew away. Because what he saw were all molecules, lines from molecules like CN, CO, CS, very simple molecules, but still there. But every one of those molecules occurred in more than one form. How many forms of CN can you have? It's one C, one N, that's it. It turns out that carbon can be 12 carbon, 13 carbon. Or 30 carbon to be aware. There's only one 100 carbon atoms in the universe is 30 carbon. Nitrogen can be 40 nitrogen or 50 nitrogen. But only one out of every 1,000 nitrogen atoms is 50 nitrogen. What he saw was CN, yes, but also 13 CN and C15N. He even saw 13 C15N. So all these very rare isotopes are enormously abundant. Something very strange happened. The only way you could explain it was by CNO burning. And it's a way to form hydrogen and helium using carbon as a catalyst. We carbon into nitrogen, nitrogen oxidate, oxygen falls apart, carbon and helium in the business. And that can give you sort of strange isotopic ratios. That is incomplete. But you also needed still helium burning as well, not complete, partial, to get these isotopes. So whatever had happened here, it was thermonuclear. It was a boom. Then Benedict came along. Again, I was involved with this paper. We found that the distance is wrong. We thought it was only 500 parsecs away. But he looked at our data and said, no, it is 3 kiloparsecs. They made a mistake in the velocities. And indeed, we had a mistake. That's happening in science. But if it's 6 times farther away, it's 6 squared times brighter. And so this object is much more luminous than we thought. The luminosity, now the absolute magnitude minus 12, is 10 times brighter than any nova. And so it was certainly nothing more. Outflow velocity, we also found is higher than we had seen, 2,000 kilometers per second. Plotting it up this diagram, it falls somewhere very close to this upper line. So it wasn't IOT, luminous red nova, about as luminous as they get, close to where you call them a supernova. But the merger scenario from NOAA did not involve thermonuclear reactions. So it was a different mix between a merger and the supernova. It did both. How interesting can you get? Now, these luminous red supernovae are known from extragalactic surveys. Nowadays, you look all over the sky, all the time, to look for supernovae. Why do we do that? Because supernovae use as distance. And from the distance indicator, you find how far galaxies away, you know, how fast it's moving, you find how fast the universe is slowing down. Exactly distance. It's accelerating. Remember that? The dark energy. Anything you call the word dark, it's so interesting. The dark force. Or if you live in astronomy, the dark money. I haven't spoken before. So they're constantly doing research, but they're finding other things that are not supernovae. And they found many of these luminous red novae. Many probably not as common as supernova. And what they find is that typically they have a double peak profile. First you get a peak, and then maybe 100, 200 days later the second. And the color changes. From the first one tends to be bluish, the second one tends to be reddish. And in between, you get a plateau and then it falls off. The magnitudes, actual magnitudes minus 10 to minus 15, it fits in both anyhow. And it is quite a bit brighter than novation. So these are typically called either mergers and outbursts, just like all the mergers probably are the more important. So supernova is clearly luminous red nova. Yes, it has to be. The double peak and the triple peak, okay, the models are perfect. You have 2 elements for the model. The third one is protection. The change from blue to red, because they noticed that in 1671, one object was notably red. That fits. The luminosity fits, the bipolar shell, the moment protector fits. So all of these things fit. However, the abundances do not. Because the mergers for luminous red novae do not involve nuclear explosions. It's purely conventional water. And if the event also lasted twice as long as it should, 600 days, rather than 300 people. So you wonder, can a merger lead to a thermonuclear explosion and a mini supernova? No, it suggests there is something in there, but it is supernova that star survives. And in this case, it's a merger, but it's even, it seems like both stars survived. And because of the precession. Although we haven't seen either of the stars yet, it's a bit of an assumption. I'll stop here basically and move on to the real topic. An object called PA30. We're not known for giving particularly interesting names to objects. This was the number, the 30th object discovered by Nebula. Galaxy is an energy discovery, not a professional one. There is part of a group, they call themselves the Team Sky Hunters. They hunt with telescopes and they hunt for anything that the professionals have missed. That's quite a lot. And when they find something that they look for the others archives. This particular object they found from Hawaii is an infrared satellite. With the magnetic entire sky, they found this particular object on everything else they missed. And what they do then, they try to study it, catalog it, and it's very interesting. Contact personal studies to learn more about it. But they have already themselves obtained very deep images at the professional telescope observatories. They suspected it was a planetary object value. And they have contacted them, Patrick Parker from Hong Kong, one of my collaborators, to confirm with him that it was a planetary object. This was the data. Here is the WISE image, although here there is an X-ray source added to it, that wasn't the original. So the center is X-rays, but this is the red spot that they saw, about 2 minutes across or so. And in 03, they saw a very faint, really very faint, the faintest they've ever seen in 03, nebulosity, and coincided with this one. And that is what made them think very, very faint planetary. The field is very prominent. Many fields in the Milky Way are very dense of stars. I remember once I had to quality control on the sky survey of the Milky Way. And every image that you get has 500,000 stars in it. You get the old right. And there's image after image after image. And I've never known the Milky Way so many stars. But if you think about it, 10 million decent stars, there's about one for every person. Everyone can have their own decent star. There are that many stars. Or if you prefer, there are that many people. So this is a dense field. Here is the object that we're interested in. There is a star in the center, about 50 magnitudes, not particularly bright. There is a much brighter star nearby, very confusing, 20 seconds away, but there's nothing to do with it. It's in the foreground. This causes quite a lot of problems with the observations. And there is actually another star sitting over here, only 2 seconds away, also a foreground, nothing to do, also causing some problems with those. So when they looked at it, decided to get a spectrum of the star. Saw the spectrum, found backwards, and called up Daniel to tell them that was not very interesting. Because it clearly wasn't the planetary nebula, whatever it was. And then he started to figure out what this thing was. This is the spectrum that he had. Here is the original spectrum that he got. If you correct it for rendering of the dust between us and the star, that takes away maybe the blue light. This is the spectrum that they should have seen. Had to be no dust in between us and the star. What you see is a huge bump in the blue, shorter than 4,000 meters. Ultraviolet the blue. Quite a few lines over here, broad, notably broad, and brighter, broader line over here, there's one over here, and then it peters out. And these are all different spectrum taken different telescopes, done pretty much. You've never seen anything like this. Neither did I. Contact with me to ask me the right result. I've never seen a spectrum like this. Normally, you expect to see a black body. There's a bit of deviations. Well, I can't even tell what is star and what is not here. There's so many things in there. So, taken all the confusion away, basically what we're seeing is this. And so a peak in the blue, it's individual lines on it, much brighter than the outside of that. It's more than a factor of 5 increase very suddenly. Over here, there is quite a long plateau. There's a couple of peaks, but clearly this all goes together. And there are a couple of individual lines over here. There is a bump over here. Those are the things that you try to do. So when you do that, this is research. You start to think very hard. It doesn't help. So then you start measuring things. And you look for things that I know should be there. You think, well, there's a hydrogen line at 6,000 times the density. Well, that should be somewhere over here. Where is it? Nothing there. There should be the helium line at 4471. Where is it? It wasn't there. So it turns out this star has no hydrogen or helium. Well, hydrogen is 90% of the universe. Helium is 10% of the universe. So there's nothing else. And that's more or less true. Everything else is just 0.1%. 0.1% of the universe is not hydrogen. Think about it. Yeah, you've thought about it? Let's move on. It's not a philosophy course. Yeah. So this star consisted of material that only accounts for 0.1% of the universe and got rid of everything else. You look for patterns in velocity, lines that are redshift or evolution. You can't make any sense of it. There isn't any. But these clearly it looks like the original wavelength. So there's nothing extragalactic here. It's a quasar. What is it? Some other funny objects in the distant universe. To echo the Big Bang. No, nothing like that. So I spent days and days trying to figure it out. Until I finally hit onto the thing that if you have a pattern like this, it looks like a repeating line, doesn't it? You look for what kind of lines repeat. Well, one of them is cyclotron emission. That has a couple of cyclotron goes around circles. And that is the idea. You can go around the same circle twice as fast, or 3 times as fast. You get lines that are integer ratios. So I decided to look for that. And that is when I discovered that this line over here and this line over here are exact 5 to 7 wavelength copies. If I take the wavelength scale and multiply it by 5/7, these two lines overlay exactly. You can see this one is broader than this one. That is also part of the scaling. If I change the wavelength scale, this one gets narrower and it overfits. 5/7 it works exactly. Okay, so cyclotron is this. However, I have an equation. And for every n number, I know the wavelength is a number in extra divided by n times the 1 over the magnetic field, the units of 10 to the 8 Gauss. That is very, very large. Megagauss is even bigger. 100 megagauss is enormous. So to get this kind of field, if that's my n 5 and 7, I need a field of 30 megagauss. Okay, there are some stars that have that. But if you have that kind of field on the moon, you would try to get all the glasses. And be pulled off your face. It's a bit overstated. Yeah, I like to accept it. So, but if that is the case, where is my n equals 6? So I tried to look for it, and it wasn't there. So n is 5, 7 I could fit perfectly, but 6 wasn't there. And so I had to give up. Also, since there is no other evidence that is super strong magnetic field. So I thought, yeah, I got the right 5 to 7 ratio, but the wrong reason. So then I thought, well, what else do you find these ratios? And the answer is it's in hydrogen. The hydrogen lines, remember the equation? 1 over n squared minus 1 over n plus 1 squared for the electron transits from n plus 1 to n. First year astrophysics, yeah, remember it? That has an n in it. Now, it is not obvious how I can get 5 to 7 out of this, especially since it's squared over here, but maybe I can. So I started to figure it with my mind. And I found that, yes, if I take the position as the 8 alpha and 9 alpha, so the line 9 to 8 and 10 to 9, that ratio becomes mathematically, work it out if you don't believe me, 5 to 7. So these were those lines. But of course, then to get my wavelength, I have my R, it's constant. It also depends on my Z, the atomic charge. Since I know my wavelength, I can find what charge do I need to get this. It turns out I need Z equals 8. It is nice if I have Z equals 8.23, I would have been in trouble. No proton that has that. But Z equals 8 works exactly. What is Z equals 8? It's oxygen. So this is oxygen behaving like hydrogen. How do you behave like hydrogen? By getting rid of all your electrons except for one. And then you've got a hydrogenic atom that isn't hydrogen. But for all effective purposes, you think H line. So this was a line of 08 in astronomy term, that means 7 times iron. And that suddenly I can expect to identify the curtain ring. It's in an office about 10 seconds later. And he told them he done something wrong. Because these are not lines you expect in a normal star. The energy you need to ionize oxygen 7 times is not very much higher than any star can provide. How can you do it? Well, you have to have a shock. Shock means gas moving at high speed. It hits something. The kinetic energy becomes temperature, and you get temperatures of millions of Kelvin. That is what you need to get these kind of shocked gas. So once I knew that, I could run a model. Say, what do I find? And I find that if I have a temperature of about 3.5 Kelvin, Gaussian line profiles, I could fit quite a few of these lines. The black and the blue are data. The red is my models. You can see if I peak at all the right wavelengths. Well, I don't fit this one, but I can fit this one. We've got this wing. I even get something over here. So it fits to some degree. And there are things that don't fit, but I fit all the Greek lines. I was happy with it. But no hydrogen on here. This model has nothing of that. All the lines I find are for oxygen 8, a couple of oxygen 7, neon 10, neon 9 are both present, and one line for carbon 6. It's also hydrogen. And those were the things that I found, and I couldn't fit anything else. I was not the only one. We worked in teams. Next worked in a team from here in America. He went in an entirely different direction. He said it's a standard wind. The wind without hydrogen and helium is much cooler. It can go very fast. In this case, he found it 60,000 kilometers per second. He put it through his models and he found this fit. And he found this big blue lump, as we call it, PDB, that we like to work with, can be fitted very well. And it even fits this plateau over here that I couldn't find fairly well. And so we had a big argument, was it a wind, was it my balance? We both lost. It turns out it is both. What he did find is that to get this kind of thing, he needed a star that's pretty hot. 2.4 times 10 to the 5 Kelvin. 250,000 Kelvin. This is the hottest star known. 250,000 Kelvin. Unbelievable. So what I did was I took his model, I subtracted from the data. And being part of this, I'm allowed to do that. I'm not a particle physicist, I just pretend to be one. And then plot a blind model against the residuals. I didn't change that. All I did was take this model, took it away from the data, and see what's left. And you can see now it fits the lines, this line and this line, even a bit better than before. This one still quite well. This one fits quite fit this thing over here. There is a peak at the right wavelength. The air is a bit too strong, but there is a place, I mean, you know, the plate was the Earth intercepts a part of it. The lines indicated here are all 08. And there's 2 over here as well. This one is neon 9, this one is neon 10. Count 6. So the shock gas minus the red model seems to work fine. So we're all ready to publish. What happens if someone else got their handles? Van published a paper, and it turns out to be on our website. We only found it out because we submitted our paper later. And it came back from it, so it just had a paper in press. We were too late. That was quite nice. And what he said was this star, he'd also found the same star, and had very similar data, of course. And he found there was a massive white dwarf merger product before final product. They put the abstract in the document. What it is, it was 2 stars that merged. Also, that created a star bigger than a meter mass of white dwarf. But like the star survives. There's now waiting there to stabilize. When it stabilized, it could be unstable, giving a supernova. So it was a merger going to get a supernova, but was in between. And they said it happened 16,000 years. We had some doubts about this model, but okay, because it was. What could we do? Kelvin predicted there was a rapid rotator with a field of 100 microns. And I had seen that before. However, I would show that it could not be true. Because 08, that line hydrogenic is actually sensitive to magnetic fields. And then field introduces a wave shift. I could see that that wave shift was not seen. So the field had to be 10 to 100 times less than W. The 2% of the second mass came from this luminosity. We found a slightly lower luminosity, so we didn't have it. But otherwise, then that merger, yes, it seems like he was right in there. Then Lydia Spinova came along, postdoc paper. We were still painting a cube. And she said that it is actually a version of an oxygen ion and a CO micron. Two microns of different composition, different masses. And she said, what happens if you make those together? You get a supernova type 180X, a new type of supernova. So she stacked the Nebula as a supernova. She fitted all the abundances with an X-ray spectrum and got quite a good fit on that. Even found lines from all it. From the supernova, if the Nebula of the supernova is 8, she found it somewhere between 350 and 1100. That was a number that rang a bell with us, because we had data on the speed of the Nebula. And that was accidental. We had taken the spectrum, and in the spectrum, we found lines that came not from the star, but from the Nebula. And you can see here, there is a very large velocity shift between one side and the other side. That velocity shift is almost 2,000 kilometers per second. Now, if you know that, and you know the size, you get an age. And so we assumed the velocity field, we assumed free expansion on the inner side, spherical symmetry, and we found it's 990 years old, plus or minus 250. It's agreed pretty well with the Lydia found. But at that age, was it seen? Supernova, less than 1,000 years old, should have been noticed. Could have been noticed. So this was now in lockdown, so I had nothing to do. It was very stressful to teach in lockdown, but I had to time off for my teaching. And I went through all catalogs of old novae. And the best one is by Saturn, I hope I pronounced it correctly, I probably don't. Who made a catalog of all the Chinese novae in the oldest literature. That goes back 1,000 or even longer. I went through that to find all the objects and pretty much the location of this Pakistan. And one of the two candidates, one of them I could rule out. That was Nova, didn't last long enough. But the second one was this object from 1181. And there is a whole description of it from the Chinese found where it was. Although this is some new data inserted into it. It lasted 180 days. Yeah, that is the kind of time length we found. Seen in China and Japan, listed as being in between two of their constellations, Chuanshe and Yuakari. Again, apologies for pronunciation. Visible for 6 months, bright for 2 months. And it was bright enough that the Japanese panicked. And one of the Japanese panicked said in the document, we can expect control of the administration to be lost. We blame astronomers for everything these days. But often, we find often these kind of comments in Chinese manuscripts. Not this is bad news for them. Comment appears, but often those were written down after the event happened. After the emperor had already died. They probably wouldn't dare to write it down before them. There would be brilliant death if they not have the emperor. In the manuscript, it's compared to Saturn, magnitude about 0 plus 1, so faint for supernova. It's said to be bluish red. Oh, I've seen that before. And it is said the 6 month duration really shows it's a supernova. The only problem was it was not really assigned to the remnant. Radius was called 358. The pulsar wind nebula, there's a pulsar there, there's a wind. The ionizes the wind, it makes a binary radio. It's 2 km/s. But there was a bit of doubt that it was really the counterpart of the supernova. But yes, the radio flux evolves as you expect from a young remnant. And yes, because there's no other candidate now. weak, but okay. But there are also problems. The supernova of the Pulsar Nebula seems to be around 6,000 years old, not 1,000. It is very faint for a core collapse supernova. It's what you need to get a neutron star, the pulsar. And finally, there is no remnant, no supernova, just this nebula that came from the pulsar. So none of this is entirely convincing. So we don't talk about what the constellations are. This is a map of the sky. The green one is the lunar mentioned at the supernovas. The bottom here. Here are the two constellations, and in between them, Xrays and Makai. Here is 3C58, and here is our object. And if 2 or 3 degrees error in the Chinese position, it's entirely normal. It's also seen for the planet. So either of them are possible candidates. Exactly ours is no worse than 3C. The whole problem with Chinese manuscripts is that they don't give drawings of constellations. The drawings are from once they don't always agree. So you're not always sure where this Xrays is. There are 2 possible places constellation it could be. The one here in the north is much better known, or easier to see. Now, if this object is 30 the supernova, then the star is still there. It survived the supernova. It shouldn't have. Less hydrogen and helium, so clearly something thermonuclear element. The mass is close to the 72nd mass, probably just below without opinion. And everything points at the verge. As in that very much Astronomy had said. The exposure was quite faint. We found an actual magnitude of -14, and the supernova should be -90. It's a factor of 100 below. It puts it within this blue band. So non-destructive merger explosion. What about the supernova type 1AX? Clearly related to supernova 1A, but somewhat different. They're slow and expanding, 2,000, 7,000 kilometers per second. They're faint, fainter than normal supernova should be, down to about absolutely -13. But about 30% of all type 1A supernovae at useful distances are this type. They always removed from the data before they hit the expected as they should. So clearly they are supernova-like, but there must be something else. And many models have been proposed. Accretion from a helium star, there's no hydrogen, to a massive shown white dwarf could be one explanation, triggering an explosion of the helium. Carbon deflagration, but carbon ignites not in one single explosion, but like a forest fire moving through the star. So you get all the energy without a big explosion. And that can leave a bound star at the end. The same process in a CO neon white dwarf. A merger of a carbon, oxygen, and oxygen neon white dwarf proposed, as mentioned. Just a couple of different models for these things. They predict different luminosities. If you have the diffraction model over here, that predicts a fairly luminous object. If you have the just a merger object, that gives you a lower. Our object is right in between. I'm still not separating those models from each other. Supernova came up in the fourth. It also is the merger, as I just pronounced. But in addition, while it merges, one of the stars is disrupted by tidal. It's by tidal forces torn apart. It forms a disk around the original star, and that disk ignites as a thermonuclear runaway. So we have a supernova explosion, not in the star, but in the remnants of the star that it's trying to merge. And that seems to fit the abundances that she find the elements quite well. But otherwise, it's still an unproven model, but at least it puts a thermonuclear runaway inside the merging model. So, as a bottom line, the Parker star is a very nice way of trying to test these models. Because we have the star, we have the nebula, we have measured all the abundances 1,000 years after the event. We know the exact age, and we know roughly what the life curve of the event looked like. Every 6 months, the visibility. One thing that I have learned from this is that you should not ignore historical instruments. Just because it happened 1,000 years ago doesn't mean that data isn't very useful. And the same thing for the amateur astronomers, because they learn about to found this object. professional astronomers only came in once the amateurs came out. And then the professional astronomers couldn't help it, and then they went to me. How desperate may you get? Remember those predictions? They are not. But I not use nebulae with linear velocity predictions. CK ball, we see exactly that. PM30, we don't have it. I think it's too faint to see that. The nebulae will be bipolar. CK ball shows that. Parker might be that. In that case, the bipolar axis is pointing straight at us. We can't see it. Outflow velocity is 100 to 1,000 kilograms per second. No, we find velocities twice that. Both of these are. But then we also have different energy sources. Thermonuclear bottom and the merger to make it can be explained. And the kinetic energy 10 to the 39 to 10 to the 42 joule, it's both of these are. So from that point of view, the predictions have done everything. So the transit universe is much more than just supernovae. There's more going on. There's still surprises there. But then we look at the merger. Mergers are rare, and every merger is going to be different. It makes it hard to learn from them. It is essential to learn. But it means a very cool university. CK Ball, medium island, thermonuclear, we have the impression. Pakistan, low luminosity merger supernova. That is not survived. And the bottom line is there are many surprises. Thank you. Yeah, we have many questions. I'm also happy to answer questions here afterwards. Yeah. So, I'll wear my mask. Yeah. All those records compare the brightness to certain stars. And so in the case of the brightest lights, that's a little brighter than it means. You try to make an estimate. In the case of the cramp, it was visible in the daytime. So that means that the -5 would be much brighter than that, you probably see double numbers. But sometimes it's difficult because the 1181 is compared to 7. But the problem is 7 wasn't visible in that. Yeah. So how do they know how bright 7 was? So we just made it up 0 to 1. We think that probably maybe 1 point during maybe a few months after the explosion. 7 became visible when they compared it to stars. We assume that it was accurate. In the universe, it was quite accurate. And then the other problem is it is use your eyes. But what is the filter curve of your eye? Do you know? Probably not. For yellow or green, everyone's eyes is pretty much the same. For a red light, it can be different dramatically. Some people are 2 to 3 times more sensitive to red lights than others. So if they have a red star, one person will see it brighter than another star. The second person will see it much fainter, depending on the color. So those are the problems you have to be aware of. Whenever an object is listed as very red, you have to take the magnitudes from that kind of observations with some. Okay. You probably don't know if your eye is particularly sensitive to red. Let's try to find out.
I should have a question, because most of the detailed imagery that were taken by ground telescopes, are there any detailed images taken by the Hubble spectroscope?
No, Hubble has not looked at what the Hubble could do it. Hubble is a small telescope. It's only about 2 meters across. Okay. That's for nowadays. I don't think I've used a telescope that small. Not half because I've used the Hubble. I've used the 1.9 meters of that. So it's 10 centimeters smaller. But nowadays we look at 6 to 8 meter telescopes. We've worked on telescopes of 30 to 40 meters. And so the Hubble is for an object this stage seems to be too small. Surprised?
Well, I was thinking that Hubble has also detailed imagery of variable exposures. That maybe that.
Yeah, but everything continues. objects that emit over a range of wavelengths. So you can use your filter. If you've got an object that emits at one wavelength, but that means if you have a broad filter, you just got much more confusing lighting, a lot more from your satellite. So it is not optimized for those kind of objects. And we have hard enough time even with our telescopes to get anything decent. So we looked at the Hubble and decided, no, it's probably not the right time. So the James Webb would be nice. I've got a time here for other objects, but again, James Webb is not optical. And from the models, it looked like this object is bright only in the optical and the mid-infrared. And we don't have any mid-infrared telescopes at the moment. And James Webb is just in between those. $10 billion. It's useless.
It's not useless.
Oh, yeah, I'm using it, so yes. Just fell from the money that was left over from James Webb to take every astronomer in the world out from it. So, we do wonder something.
But James Webb is specifically also sensitive in the carbon emission lines.
There are carbon emission lines around 9,000 angstroms. That fits it in the range. More important is the carbon emission lines of 150 micron. Notice it goes nowhere near that of the Sophia. The telescope that you can put on a Boeing 747. But that's quite a small telescope. I've been on that telescope. Yeah. Well, no, it doesn't feel entirely safe. You're flying 15 kilometers altitude and you open the door. Fucking in a different part of the aircraft. You don't have these documents in. And of course, this was the one flight of the entire year when they ended up having clouds above the level. So I got my data because now we didn't get this. And you have to take your passport out, sir.
Why?
Because you don't know which country you're in when you land. If there's an interruption, if you land somewhere, it could be in Canada, it could be in Mexico. They don't fly to Mexico, safety reasons. Yeah. But yes, we need to have a passport with us in case we land in Canada. And you need security clearance on NASA, but that was easier. In our galaxy, you might expect a merger about 1 million. Most of them will be very just a planet falling into a star. A merger between two stars, maybe once a decade, once a century. So it's pretty rare. It won't happen to ourselves.
Okay, if there are no more questions, we can dismiss. Thank you to Professor Albert and Professor Snell. If you have any questions, you can find Professor Albert directly. I can ask. Great, thank you.